Okay, so the last lesson of the school year, we are going to be, just the first one, we are going to be looking at the solubility of salts. Now this is something that we're already a little bit familiar with because we talked about solubility of ionic compounds earlier in the school year. We talked about ionic compounds that are considered to be completely soluble in water. And then we said that everything outside of that list was insoluble. That's not entirely true. Everything that we excluded outside of that list of soluble ionic compounds is not necessarily insoluble. They might only be partially soluble. And so we're going to look at that piece today, how we can look at the solubility of a salt and really determine how soluble is a salt if it's not considered to be completely soluble, like the ones that we talked about with that list earlier this school year. Yeah, one of these. You'll get those a lot. You'll get exceptions a lot as you continue into a college chemistry course. You'll have your college professor say stuff to you like, you probably learned in general chemistry that, fill in the blank, but that's not really true. And so you'll get this as you continue. Yep, right here. All right. Some ionic compounds, which we refer to generally as salts, are completely soluble in water. This means that when we dissolve that ionic compound in water, that ionic compound will completely dissociate into ions. For example, sodium chloride. When sodium chloride is dissolved in water, it completely breaks up into sodium ions and chloride ions. Every single unit of NaCl breaks into sodium ions and chloride ions. So when all is said and done, we have a solution of sodium ions and chloride ions. Some ionic compounds are only partially soluble in water. This means that when we dissolve those ionic compounds, some of the ionic compound will dissolve and some will not. What we eventually get, because some dissolves and some does not, is an equilibrium that is established. An example of this would be barium sulfate. We looked at solubility rules at the beginning of the year. We determined that sulfates were generally soluble except if with, and barium is one of those exceptions. So barium sulfate, we determined earlier this year, is insoluble, when in fact it's partially soluble, meaning it's not good at dissolving in water, but it can to some extent. So when we put barium sulfate in water, an equilibrium will be established. Some barium ions will form, and some sulfate ions will form, but there will also be barium sulfate remaining. And so we'll have this constant conversion then of barium sulfate converting to barium and sulfate ions and barium ions converting to barium sulfate. Now, because this is an equilibrium, we can write an equilibrium expression. KEQ is equal to the concentration of barium ions times the concentration of sulfate ions. Both of these have a 1 in front of them, so both of these are raised to the first, or just themselves. Now, just like with Ka and Kb, this has a special name. This is called Ksp, which is referred to as the solubility product constant for salts. Ka refers to the equilibrium established when an acid is dissolved. Kb refers to the equilibrium established when a base is dissolved. Ksp simply refers to the equilibrium that is established when a salt is dissolved. It's all found the same way we find Keq, the ratio of the products raised to their coefficients over the reactants raised to theirs. But we have a special name for it because it specifically refers to salts dissolving in water. Questions? What would a high value of Ksp indicate? A higher Ksp compared to a lower value of Ksp. High Ksp indicates a higher solubility. And low Ksp indicates a lower solubility. Just like Keq indicates the extent of a reaction, Ka indicates how strong an acid is, Kb indicates how strong a base is, Ksp indicates how soluble a salt is. The higher the Ksp, the more ions that are formed. The more ions that are formed, that means that the salt has to be more soluble. So we can use Ksp to compare the solubility of salts. If something has a higher Ksp, we can say that's more soluble in water, a lower Ksp, that's less soluble in water. Let's look at making some calculations. We're going to do two types of problems today relating to this idea. The first is calculating Ksp. Given solubility information. We'll look at two problems here. The first, copper 1 bromide has a measured solubility of 2.0 times 10 to the minus 4th molar. And we want to use that to find Ksp. And then bismuth sulfide has a measured solubility of 1.0 times 10 to the minus 15th molar. Find Ksp. What the solubility tells us is how much we could dissolve of that substance in 1 liter of water and have it entirely dissolved. So we could only add 2.0 times 10 to the minus 4th moles in 1 liter of water of copper 1 bromide. So only 2.0 times 10 to the minus 4th moles. It's not very many moles, right? It's a very small amount of copper 1 bromide in 1 liter of water and have it dissolved. So that is the maximum amount of copper 1 bromide that can go into 1 liter of water. Bismuth has a much smaller solubility. We can only dissolve 1.0 times 10 to the minus 15th moles in 1 liter of water. What kind of Ksp value should I see for number 1 compared with number 2? This one should be a lot bigger than this one because this one has a much higher solubility than this one. So let's think about this. What if we dissolve copper 1 bromide, CuBr, in water? So we take solid copper 1 bromide and dissolve it in water. It'll form copper 1 ions and bromide ions. If we take that exact amount and dissolve it in 1 liter of water, we have what's called a saturated solution. We've dissolved as much of the salt in water as we possibly can. If we try to add any more, it just simply won't dissolve. So we're going to see if we can figure out at that point, what would the concentrations of these be? And that's what we'll use to calculate KSP. KSP will be equal to the concentration of the bromide ion raised to the first times the concentration of the copper ion raised to the first. So if we can figure out what the concentration of each of these are when we've dissolved 2.0 moles, 2.0 times 10 to the minus 4th moles in 1 liter, we can calculate KSP. Well, if the solubility of the copper 1 bromide is 2.0 times 10 to the minus 4th molar, and this breaks up in a 1-to-1 ratio, wouldn't we have an equal amount of copper 1 and bromide ions in solution? Okay, and again, I know that for some of you, this is a hard thing to imagine, but imagine this being the 2.0 times 10 to the minus 4th moles of the copper 1 bromide. And I'm going to stick it in 1 liter of water. When I stick it in 1 liter of water, because it is soluble with that much, it'll break up in a 1-to-1 ratio. So wouldn't I have 2.0 times 10 to the minus 4th moles of copper 1 and 2.0 times 10 to the minus 4th moles of bromide ions in 1 liter of water? So the amount of copper 1 and the amount of bromide ions in that solution would be equal because it breaks up in a 1-to-1 ratio. So this is also 2.0 times 10 to the minus 4th molar. And this is 2.0 times 10 to the minus 4th molar. Well, then all I have to do is plug these numbers in. So KSP be equal to 2.0 times 10 to the minus 4th times 2.0 times 10 to the minus 4th. What is KSP, copper 1 bromide? Four point zero times 10 to the minus 8. All right, let's see if we can compare that to this bismuth sulfide solution and verify that the KSP for copper 1 bromide is indeed much larger than the KSP for bismuth sulfide because the solubility of copper 1 is so much greater than the solubility of bismuth sulfide. So again, we're going to write a reaction for dissolving bismuth sulfide in water. Bismuth ion has what charge? +3. Sulfide ion has what charge? -2. So we need 2 of these and 3 of these to write the formula for that ionic compound. So when this solid is placed in water, it will form 2 bismuth ions and 3 sulfide ions. Yes. Oh, thank you. Go ahead. Now, if the solubility of this is 1.0 times 10 to the minus 15th molar, that means we can dissolve 1.0 times 10 to the minus 15 moles in 1 liter. When we have that saturated solution, how much bismuth and how many bismuth ions and how many sulfide ions would we have? Well, think about this, guys. Let's say this represents my 1.0 times 10 to the minus 15th moles that I'm going to put in 1 liter. It's going to break up into 2 bismuth ions and into 1, 2, 3 sulfide ions. Don't I have twice the number then of moles in 1 liter as I originally started with of bismuth ions? And 3 times the number of moles I originally started with of sulfide ions? So how would I find the concentration of this when I create this solution? Yes? Yes, so 2 times 1 times 1.0 times 10 to the minus 15. So this will be 2.0 times 10 to the minus 15. And this will be 3.0 times 10 to the minus 15 molars. Now to calculate KSP, KSP is equal to the concentration of the bismuth ion raised to the second times the concentration of the sulfide ion raised to the third. So KSP is, 2.0 times 10 to the minus 15 squared times 3.0 times 10 to the minus 15 cubed. It's a really little number, really little. Okay. Because KSP is found by the ratio of the products raised to their coefficients divided by the reactants raised to theirs. And that's by definition of how we find KEQ, or in this case, KSP. So we need to take the bismuth raised to the second, the sulfide raised to the third, but their concentrations in that solution are twice and 3 times what we initially put in of this because of the way that they break up in the balance equation. Yeah, Connor? Yes, sounds about right to me. KSP is much, 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 much smaller for bismuth sulfide than it is for copper 1 bromide, indicating that copper 1 bromide is much more soluble than bismuth sulfide. We can also obviously see that with the solubility of them. Okay, the other type of problem that we're going to look at is what if we're given KSP and we want to find solubility? So the opposite of what we just did. So calculating solubility given KSP. We're going to do 2 problems. Calculate the solubility of a saturated copper 2 iodate solution if KSP is 1.4 times 10 to the minus 7th. Calculate the solubility. This should say calculate the solubility of copper 2 iodate in a saturated solution. Calculate the solubility of hydroxide ion in a saturated solution. Magnesium hydroxide solution. If KSP is Hang on, I have to look at this one. (5.6 times 10 to the minus 12). All right, well, let's first write out what happens when we dissolve copper 2 iodate in water. What is the formula for copper 2 iodate? Well, copper 2 is Cu plus 2. What is the iodate ion? IO3 with minus 1 charge, so we need 2 of those. So when that's dissolved in water, we're going to get 1 copper 2 ion and 2 iodate ions. And we want to know the solubility of the copper 2 iodate. So that's X. Well, what are the concentrations of the copper 2 and the iodate ion relating to X? What's the concentration of the copper 2? Isn't it the same as this because this is a 1-to-1 ratio? So wouldn't this also be X? And what would this be? 2X. So we know that KSP is going to be equal to the concentration of the copper 2 ion times the concentration of the iodate ion squared. And we know that this is X, and we know that this is 2X, and we know that KSP is 1.4 times 10 to the minus 7th. That means we can solve for X. So 1.4 times 10 to the minus 7th is equal to X times 2X squared. What is 2X squared? 4X squared times X is 4X cubed. So 1.4 times 10 to the minus 7th is equal to 4X cubed, and then we can solve for X. And X is what we're looking for, the solubility of the copper iodate. So what is X? KSP is the solubility product constant, and it's based on the solubility of the salt. The solubility of a salt is how much of that could dissolve per 1 liter of water. KSP then looks at, well, an equilibrium is going to be established when that happens, and it's based on the solubility, but it's essentially just another way to look at, just like we talked about Ka. Well, we could actually compare, like when we look at acids, when they ionize, we could actually compare how much hydrogen ion is produced by the acids and use that to rank them in terms of strength. Just like we could look at the solubility, but we can also use Ka and KSP for the same, to do that same thing. What is X? .0033 molar, or moles per liter. So the solubility of this is 0.0033 moles per liter. That means you can dissolve 0.0033 moles in every 1 liter. Let's take a look at this last problem here. So we have magnesium hydroxide, MgOH2. We're going to dissolve that in water. We'll get magnesium ions and hydroxide ions. If the solubility of the magnesium hydroxide is X, what would the solubility of the magnesium ion be? And what about the hydroxide ion? 2X. So we can use this to figure out what X is, and then ultimately to figure out what the solubility of the hydroxide ion is. We know that KSP is going to be equal to the concentration of the magnesium ion raised to the first times the concentration of the hydroxide ion raised to the second. We can plug in x here, 2x here, and then we can plug in 5.6 times 10 to the minus 12 here. So 5.6 times 10 to the minus 12 is equal to x times 2x squared. So again, we have 5.6 times 10 to the minus 12 is 4x cubed. And we can solve for x by dividing by 4 and then taking a cubed root. When I solve this, I get x is equal to 1.1 times 10 to the minus 4th molar. But is that the solubility of the hydroxide ion? What is the solubility of the hydroxide ion? 2x. So we need to multiply this by 2 to actually calculate the solubility of the hydroxide ion. So it'd be 2.2 times 10 to the minus 4th molar. Questions, comments, concerns? Madison? Because we're looking to calculate the solubility of the hydroxide ion, and that is 2x. We just calculated what x is. We need to know what 2x is if we want to know the solubility of the hydroxide ion. And mathematically, guys, if you guys went in and plugged in these numbers here and x here, you'll get the value for KSP. Any other questions? Okay, take out your practice test, and the last page of the practice test, number 8. I'm again being kind, and I'm going to eliminate a small part of the curriculum because I know that you guys have a lot on your plates right now. With doing that, I'm not going to talk about we're not going to talk about predicting precipitates, if precipitates will form or not. So I want you to cross out number 8 on the very last page. That is a problem that you will not be able to do because we will not spend time talking about that. And then as of now, you can do the rest of your practice tests, and this is the conclusion of the material for the school year.